All right, triangle-based word problems, related race problems, that is. I've already worked some of these in the previous chapter, in the previous video, where we sort of did some abstract ones where they'll talk about a triangle or whatever. Whereas usually in this type of problem, the slightly harder ones, we'll still be using the same formulas and doing the same derivative process and writing down our givens and stuff. Everything's exactly the same. The only trick is that we'll have to do a little bit of work on the front end of the problem at the beginning to sort of figure out a diagram for the problem and sort of label stuff, because they're not just going to give us the triangle usually. We're going to have to create a triangle situation and realize that a triangle is what to use or whatever. So let's take a look and you'll see what I'm talking about. Alright, so here's a classic one, plane flying overhead. I made it a model airplane just to keep it a little bit more fun, but basically, guy's standing on the ground, plane is zooming over his head, and all he's got to tell how fast it's going is a radar gun. But the problem with radar guns, if a car is coming, and this is why the police always park right by the side of the road if they're trying to tell how fast traffic's going. A radar gun just tells you how fast something's coming directly towards it. But if something's sort of shooting off to the, driving by it off to the side, it's not going to read the actual speed of it. It's just going to read how fast that object's getting closer to it. But, so if we have a plane flying overhead, like this, in that direction, but an observer is down here on the ground, looking up at it, his radar gun is going to tell us how fast this distance is changing, not how fast this distance is changing. In other words, it'll tell the velocity directly towards him, but since the plane's not going towards him, the radar gun's actually going to read low. It's going to read slow. You don't actually have to know that. All you have to realize is the radar gun is going to read something other than the speed the plane is actually going. And it's going to, and in this case, and I think whenever you see one of these problems with the radar, it has to be a constant height. Like the plane can't be swooping or taking a turn or something. And it says the plane is 30 meters off the ground. So this is 30 meters. And it says at the moment this is 40 meters away. But we're going to need a variable because this plane is moving, right? So we wanted to have a variable, like, I don't know, maybe this is x. Because that way if we give the plane's position a variable name of x, then the derivative of that, when we take the derivative, will give us the rate of change of that thing, which is the speed of the plane, which is what we want. And then the radar gun, in case you haven't figured it out yet, that's the hypotenuse. So maybe call this h for hypotenuse? I don't know. So if you saw that previous video, you might realize, there's probably a Pythagorean situation. There's no angles mentioned. They didn't mention the angle that the gun is looking at the plane or anything. In that case, we'd be using SOHCAHTOA instead. But since no angles are mentioned, we're just going to go ahead and use Pythagorean. So let's take a crack. If we're planning on using Pythagorean, and these are our letters, what are the givens? They gave us that it's 30 meters off the ground, so that's fine. When they are 30 meters off the ground and 40 meters away, so they basically told us that they want to know the plane speed when x equals 40 meters. And I don't know what else we got. Oh, the planes are going, the radar says the plane is going 20 meters per second. But that's what they're asking for, right? They're saying estimate the plane's speed if the radar gun says 20. So the radar gun says that dH/dt, because you got to realize that dH/dt is what the radar gun is telling you, is 20. And the plane's actual speed is going to be different than that. Might be higher, might be lower. I think it's probably higher, but let's see what happens. So at this point, we've got some givens, we've got some letters, and we want to use Pythagorean, so let's just go ahead and plug into the Pythagorean. X squared plus 30 squared equals h squared. And as always with related rates, we're going to take the derivative with respect to t. Alright, so 2x dx dt, and then derivative of 30, or 30 squared is just 0, equals 2h dh dt. Alright, so right away I can see the 2's are going to cancel. And then they asked me for what? Estimate the plane speed. So I want dx dt. So that means I'd like to have dx dt by itself. So I'll just divide both sides by x. Then I'll put it on the other side. So I'll get dx dt equals h over x times dh dt. And that, of course, is just one number. So I think we can plug in. Let's see what happens. Uh-oh. What's h? I already need to plug in h, but I don't have it. So where am I going to get h? Well, it turns out we can calculate h because we know that x should be 40, because they're asking us to find all this stuff at the point that the plane is 40 meters away from the guy. So when x equals 40, if that's 40 and this is 30, doesn't that mean that h equals 50? Just because it's sort of like a 3, 4, 5 triangle. So h is 50. And then we got dh dt, which is 20. Yeah, right there. All right, so when we multiply all that out, we get 25. And that's going to be meters per second. All right, pretty cool. If they had asked us how, at what rate is this angle changing or something, like how fast does the guy have to look or something, then we could probably figure that out too, because we just used SOHCAHTOA, so we'd have that the sine of theta equals opposite over hype. And you notice they just asked us, hey, how fast is this changing? Well, all you have to do now is take the derivative of this, and so sine theta opposite is x, hypotenuse is h. So you can see that if we want to take the derivative now, take the derivative of sine theta, we'd get cosine theta d theta dt. And this is actually the thing that we'd be solving for, because I just asked you, hey, how fast is the angle theta changing at this point in time? Cosine theta would be able to figure out, because cosine theta is just going to be 30 over the hypotenuse, which is 50. And then, of course, derivative of x over h is a quotient, which is a bummer. So that'll be h dx dt minus x dh dt all over h squared. Now, I'm not going to bore you with plugging all that stuff in, but suffice it to say, we can find everything here. Cosine theta is just going to be 30 over 50, because it's adjacent over hypotenuse. H we know is 50. Dx dt we know is, actually we just solved that, right? Dx dt, we would need this 25 right here to plug in for dx dt right there. X we know is 40. Dh dt we already know is 20, because that was in the original given. And h, of course, we know is 50, so we can plug in h squared. Pretty exciting stuff. Yeah, d theta dt. And the units on that are anybody's guess. I'm guessing radians per second, but we'll see what happens. All right, Pythagorean ladder example. So there's another Pythagorean problem, except this time it's a pretty common scenario actually in these problems where they have some flat object that's sort of like, if a ladder's leaning up like this and then it starts to fall, my elbow slides along the ground as the ladder slides down the wall. So that's like a really common type of problem. And if you look at a typical calculus book, there'll be 10 problems that are like that exact same thing happening, only all these different things like, oh, there's a rope pulling a ladder up a wall, or the ladder's falling this way, how fast is something changing? Anyway, so there's a bunch of ways to ask this, but they all kind of work out the same. It's a Pythagorean problem with a constant hypotenuse, because a 10-meter long ladder is leaning up against a UPS truck. So UPS truck, doesn't matter, vertical wall, ground, right angle, and the ladder's leaning up. And they've told us it's a 10-meter ladder. Then it comes to truck, thing begins to slide as usual. The base of the ladder is sliding away from the wall at 0.5 meters per second. So if this is x, they've just told me that dx dt equals 0.5 meters per second. Now that's a really important thing. If they give you the rate of change of something and you don't have that letter on your diagram yet, you better put it on your diagram, because otherwise, how are you ever going to plug in dx dt to your formula unless there's an x to begin with to take the derivative of? And of course, and this has to be a variable anyway, because as the ladder slides down, that distance is growing. And of course, so is this one. As the ladder slides down the wall, its height between itself and the ground is getting shorter. And we also know we need a y, or we need to name this variable something, because the question it's asking is, how fast is the top of the ladder sliding down the truck? So basically asking for dy dt. So that's another reason we'd have to have a variable that sort of quantifies that distance between the ladder and the ground, so that we can figure out its rate of change. All right, and then they said when it's 6 meters from the ground. So they told us y equals 6 meters. So I think that's all we got to do is plug in Pythagorean. So the only difference between this problem and the previous one is that the side that's fixed is the hypotenuse. So we're going to have x squared plus y squared equals 10 squared. So we got 2x dx dt plus 2y dy dt equals derivative of 10 squared, that's just 100, that's nothing. So you want to be real careful. I've seen students sort of try and use the power rule on something like this, but 10 squared is just 100. Derivative of a constant is always 0, no matter how big the constant is. All right, so we got this. At this point we can solve. The 2's are going to cancel as always. Now you'll notice that pretty much always happens in Pythagorean problems, and it's already happened on the 2 we've worked here. But we want to solve for dy dt. So I want to get this by itself. So that means I'll subtract this term from both sides, the x dx dt term, and I'll get that y dy dt equals negative x dx dt. Now you might be thinking, hey, that negative sign must be a screw up. What went wrong? Well, actually, it kind of makes sense that if this tip, the ladder is going down the wall, that means y is getting smaller. So its rate of change is negative. And let's see, we're asking for dy dt, so we want to get this by itself, get rid of the y, so we'll divide both sides by y. So those cancel. All right, so now we just plug in, because we need negative x over y dx dt. So negative x, what is x? Oh man, I have the y equals 6, and I have the dx dt equals 0.5, but I don't have x. But of course, just like with the other Pythagorean problems, I can get that from the original. So if I know that y is 6, then once again we got a 3, 4, 5 deal here, but if you just work Pythagorean, you'll get that x equals 8. I'll write that down here, just for kicks. Alright, so negative 8 over 6 times 0.5. 2 goes into that 4 times and 3 times, so negative 4/3 times a half is 2/3. So we get negative 0.667. And what are the units on that, in case you're curious? It's got to be meters per second, because everything else in this problem is meters and seconds. Alright, cool beans. Pythagorean, pretty sweet. Interestingly, we have yet another Pythagorean problem to do. What a shock, right? These just come up all the time. 2 roller derby teams racing around a figure 8. Figure 8 is just where you go, you know, it's like a demolition derby kind of thing, where the two, as you do laps, you have to go through an intersection, but so are the other people, so there's a chance to collide. So these roller derby teams are going around, whoa! And obviously as they keep going around like this, they can crash right here if two teams are coming in different directions. I'm just going to assume that that is perpendicular. Oh, they said perpendicularly at the center. So these two tracks come in at right angles to each other. That's obviously great information to have, because that allows us to use Pythagorean or SOHCAHTOA. All right, so let's take a look what's going. So we got one team coming this way at 15 meters per second. And we got another team coming this way. Doesn't matter which two ways you have them. Point is they're going to be hitting at a 90-degree angle. So we have a 90 right there. So if two teams are coming at 15 meters per second from two different branches, what is their closing speed relative to each other? So this is kind of like that airplane problem, when what we really care about is not how fast they're heading towards the center, but how fast they're heading towards each other. It's kind of like the head-on collision. You know, if one car, let's just switch out of this situation for a second and think about a street. If a car is driving at 30 miles an hour this way and hits a brick wall, it just hits the brick wall at 30 miles an hour, right? But if a car is coming the opposite direction, also at 30 miles an hour, and they crash head-on, the velocities add up. So that would be sort of like a 60-mile-an-hour crash, because 30 plus 30 gives you 60. So that's sort of like the relative speed there was 60 miles an hour relative to each other. So the question here is, instead of coming straight on, what happens when we're colliding at an angle like this? Obviously, it's going to be worse to hit somebody that's moving than someone who's still, but it's not as bad if they were going in the same direction or opposite directions. So the answer won't be 30. It'll be less than 30, probably bigger than 15. But I would suggest we probably have a Pythagorean problem, because just like if we just call this hypotenuse h, then dh dt, the rate of change of that hypotenuse getting shorter, is how fast the two teams are coming towards each other. And once your hypotenuse gets down to 0, that would be the moment of impact. So h is really the key variable here. And I guess we'll call this team X and this team Y. You know, their distances from the intersection. And X equals Y, right? That's really important on this one. Anyway, so we'll just do Pythagorean. So X squared plus Y squared equals H squared. And let's just write down our givens real quick. Each team is traveling at 15. So dx dt equals 15. Yeah. Couple of bad 5s right there. And dy dt also equals 15. And what else we got? That's it. Okay, so just take the derivative as always. And you notice this time we don't have any constants. So we have to take the derivative of all three terms. So we get 2x dx dt plus 2y dy dt equals 2h dh dt. Alright, so here's the thing I'm solving for, because I want to know dh dt. I want to know the closing speed. But what about all this other junk? See, I've got dx dt, I've got dy dt. Do I have h? No. Do I have y? I don't really have any of these, do I? That's kind of weird. Well, let's see what happens though. I know that x equals y. So actually I could just get rid of this y and turn it into an x. So I know x equals y. So that just narrows down to one less letter to worry about. What about h? Well, hey, wait a minute. Isn't this a 45, 45, 90 triangle? So that whatever x is, x equals y because it's an isosceles right triangle. And then we've got a ratio. We know that h equals the square root of 2 times x. Because the hypotenuse in a 45, 45, 90 is just square root of 2 times the leg. So couldn't I just replace this h right here with a square root of 2x? Let's do that real quick. 2x dx dt plus 2x dy dt equals 2. And then I'm going to replace this h with square root of 2 times x dh dt. Oh. Do you see what magically happens? I still don't know when to plug in for x. And the truth is that when this collision actually happens, x is going to be 0 anyway, right? H will be 0, x will be 0. There won't be a triangle left because at that point the two teams are on top of each other. But what we want to, the way we're going to estimate the speed then is how fast they're getting closer before the impact. And at any given moment I can look at 2 seconds before impact, 1 second before impact, 0.1 seconds before impact. As they get closer and closer, it turns out that the ratio between everything stays the same, and that's why these x's are in every single term. And what are they going to do now? They're going to cancel out. And if you've taken physics ever, you've probably seen some situations where there's like a problem where they don't give you the mass in a problem. So talking about a mass sitting on a hill doing whatever, they don't tell you mass always, but almost always when they don't tell you mass, m's going to end up showing up in every term and canceling out. And that's what happened right now with x, and actually always also happens with 2's. So at this point, we've got that dx dt plus dy dt equals square root of 2 times dh dt. So let's start plugging in. dx dt was 15, dy dt was 15, and now I just got to divide by root 2 to get dh dt. So 30 divided by root 2. We don't have to rationalize this. Well, we could. I mean, 30 over root 2. But then you could rationalize it if you don't have a calculator. But if you do have a calculator, this works out to 21.2. And since all the velocities were in kilometers per second, that's what that is. All right, pretty awesome. Let's check out another problem. All right, so here we got an equilateral triangle, and we want to know how fast the height is changing. Now, this seems like a pretty generic question. Should have been the last video because this isn't like a real-world situation. But what I want to show you here is that there's actually a trick in here. That we're asking for the height, the rate of change of the height, but the height isn't really something you normally associate with a triangle. The side length is probably going to be x. So an equilateral triangle is x by x by x, 3 sides of x length, and yet we're asking for height. They're asking for dh dt. So that's kind of wacky. This is going to actually be the first we'll see of the two-step problems where we have to sort of combine variables and stuff to see how things work out. All right, so the edges of a triangle are growing at 2 centimeters per second. So they're telling us that dx dt equals 2 centimeters per hour. It's a slow triangle growing. when the sides are 4 centimeters, how fast is the triangle's height growing? All right, so they're asking for DHDT. So the most obvious thing to do is, they told us how fast the edges are growing. What about the height? So this is kind of weird. I don't see any mention of area. And it's not a right triangle, so I can't do any Pythagorean type stuff, or SOHCAHTOA even. But the height, So I'm just kind of lost right now. I don't know exactly how it's going to work out. But I know they asked for height. And height is not currently on my drawing. So what I should do is, I'm going to draw in the height. And just word to the wise, whenever you see an equilateral triangle, you should be thinking to yourself, or you just have it in the back of your mind, ready to pull to the front of your mind, that an equilateral triangle is a 60-60-60 triangle. And when you split it in half, you get a 30-60-90. That's really useful, obviously, if you want to work with ratios, because that means that this side just right here is just half that bottom, so it's x over 2, which makes this side right here x root 3 over 2 is h. All right, so we got that done. Let's see what we could do. All right, so they didn't ask for area, didn't ask for volume, didn't ask for any obvious other formulas we could plug in. Hey, wait a minute. If I took the derivative of this, would that give me something with all the variables I want and all the ones I need? Because it's got an h in it, which means it'll have a dHdt if I took the derivative. And it has an x in it, which means I'll have a chance to plug in these two guys, or at least one of them. Let's see what happens. Yeah, so let's just try differentiating h equals x delta 3 over 2. We'll take the derivative with respect to t and see what happens. dh over dt equals, now square root of 3 over 2 is really just a number out front, it's a coefficient, so we'll just leave it square root of 3 over 2. And then the derivative of x is dx dt. All right, so I feel pretty good about this. I've got all the letters I'm given and the letters I need, except for x. You'll notice they have not given, like right now I don't have a place to plug in 4. So that is a little weird, but everything else made sense about this, and since there's no squareds anywhere, that x is going to go away when I take the derivative. So it makes sense that there's no x, given the derivative I just took. It's not like I forgot to put in something to my formula. Well, it turns out that since all this is, it doesn't matter how big the 30-60-90 triangle is, just whenever you have a 30-60-90, where one side is growing at 2 centimeters per hour, it's going to be a constant ratio. So this thing is going to have a steady rate of increase, and that's why x doesn't matter in this case. Anyway, that point aside, there's just one of those rare examples where they gave you some information that didn't end up being used. But we got lucky, and taking the derivative of something else gave us what we needed. So let's plug and chug, square root of 3 over 2. And then dx dt, they told me is 2. And that was centimeters per hour. The 2's cancel, and I just get square root of 3 centimeters per hour. And does that make sense? How fast is the triangle's height growing? Centimeters per second makes sense as a unit. So there you go, wacky. So in that one, they didn't give us any of those buzzwords we're always looking for, like volume, area, surface area. Usually there's something like that where you can just know exactly what formula to use. This one, which took advantage of the fact that whenever you see an equilateral triangle, when in doubt, split it in half and turn it into a couple of 30-60s. Nice. All right, similar triangles. Now this is a hard problem, so if you're not in, if you don't have a very mean teacher, you might not end up doing this one. It's sort of a classic, and they've got all different kinds of, different books and different teachers ask it different ways. But the point is we got similar triangles we're dealing with. And the thing to remember about similar triangles is that they have some ratios, right? So first things first though, let's draw a diagram. Now I think we've all been in this situation where it's like, it's late in the day, the sun's coming in, pretty sideways, and you see that your shadow is very long, right? So you could be like 5 feet tall, but your shadow is 20 feet tall because the sun is so low in the sky. Well, in the case of a street lamp, as you walk by the street lamp, it's almost like the sun is setting really fast. As you walk away, your shadow gets longer and longer, kind of crazy. So what we'll do is we will draw a similar triangle situation like this. So what is going on here is this is the street lamp. So here's the sun shining, or the light shining. And here's our guy. Let's figure, you know what? The tip of his shadow is going to be the tip of his head, right? So a little ray of light that comes out of the light is just barely going to glance the top of his head, and that'll be the tip of his shadow down here. And these will be right triangles because the street light is straight up and down and the guy is straight up and down if he's walking. And the height of the street light, we're given a couple of heights here. We got a 2 meter tall man, so that's 2 right there, and then a 5 meter tall light. Alright, so pretty good so far. He notices his shadow is moving pretty fast. He's strolling at 1 meter per second. Okay, so I'm not sure where to plug that in yet. And they want to know how fast the tip of his shadow moving. So it looks like we have two unknowns. We have the man's speed, and they gave it to us, but where's that letter go? We need some letter that's going to represent his speed. And obviously on the physical diagram, you know, the speed at which he's walking is going to be the derivative of something. But what's it the derivative of? It's the derivative of his position. So if you just, you know, say, hey, you know, maybe that street light was at the origin, 0, 0. So x is just going to be his coordinate. The derivative of that is going to be how fast he's walking. And then the other thing we want to know is the thing we're solving for. So dx dt, how fast he's walking, is just 1. Then how fast is the tip of his shadow moving? So for that one, we need another variable that represents the tip of his shadow. And maybe that's this guy right here. So that whole length is y. You know, I'll call it y. What the heck? So what they're asking for is dy dt. They want to know how fast is the tip of the guy's shadow moving, given that he's walking at 1. So I think there's a scenario. We've got two variables. Dx dt we're given, and dy dt we want to know, and they've told us that he's 8 meters away from the streetlight, so x equals 8. So it looks like I have a lot of good information here that I could plug into a formula if I knew what to take the derivative of. But since these are similar triangles, let's go ahead and use a similar triangle deal. And there's a lot of different similar triangle ratios, but the point is just corresponding parts. So what I'm going to do is I'm going to take the ratio of the shorter leg to the longer leg. So the ratio of 5 to y on the big triangle has to equal the ratio of 2 to the longer side of the smaller triangle. But wait a minute, I don't actually know this length right here. This length, I don't have a letter for that. I have an x and I have a y, but x is something else. It's over here. So do I need to make up a whole new letter at this point? I don't actually want to do that, because if I add another letter, I've already used all my letters, I used all my information, I don't want to just conjure up another letter. Is there something else I could call this? Well, isn't that just y minus x? So when in doubt, you know, try and label a new distance as like a sum or difference of other things you've already got on the drawing. So if I do that, then I've just got y minus x right here, and I think that'll help me out a lot, because now I have something I could take the derivative of, this ratio. If I just cross multiply, we'll get that 2y equals 5y minus 5x. So take the derivative of that, and we'll get, well actually we can combine stuff. We'll get that negative, subtract 5y from both sides. I'm going to work it over here. So we get negative 3y equals negative 5x. Make those positive, take the derivative. So we'll get 3 dy dx, dt, sorry, dy dt equals 5 dx dt. And then the thing we're looking for is dy dt. So if I just divide both sides by 3, here's my formula. So I got dy dt equals 5/3 dx dt. Does that help me? Dy dt? Yeah, it looks good, because I have dx dt as 1, and I got my 5/3. This is yet another problem where we didn't use a piece of information. We did not use the fact that he's 8 meters away. This x equals 8. There's no space for that. But what that means is that when a guy's walking away from a street lamp, the tip of his shadow is actually moving at a constant rate. It looks like it's sort of accelerating away from you, but really it's just going faster than you are, so it's getting further away from you, but it's just getting further away at a constant speed. If you're walking at a steady rate, your shadow is also walking at a steady rate. It's just walking faster than you are. So 5/3 times 1 is just going to equal 5/3. Cool beans. All right, and then sort of a secondary question we could ask here. How fast is the length of a shadow increasing? The length of a shadow is just this y minus x, right? So that 5/3 meters per second, that's how fast the tip of his shadow is moving relative to the street light. But the other question is, how fast is this shadow growing? So just y minus x. So one way to do that would be to say, hey, if I want to know how fast something is changing, I just take the derivative with respect to t of it. And the thing I want to know how fast it's changing is just y minus x, right? I want to know how fast that difference, y minus x, is changing. So that's just going to be dy dt minus dx dt. If I take that derivative, and that is dy dt, which is 5/3, minus dx dt, which they gave me as 1, and that's just going to equal 2/3 meters per second. All right, interesting. There's another way we could have done it, which is said, you know what? This is going fast, but this is also moving, so the way you get the relative speed is you just subtract the two. But again, that's what we did, 5/3 minus 1. So the point is, anytime you want to take, find the rate of change of something, just take the derivative of it with respect to t. Excellent. All right, so triangle strategy summary. Make a drawing that's super important. And you'll want to label the drawing with letters. So you'll need to pick things, the various letters that you have in the problem. You'll need to pick letters for each of those quantities, like maybe x's distance or y's distance. And then for things like speed and stuff, those will be the derivatives, right? So that'll be the rate of change of x is dx dt. The rate of change of y is dy dt. And you want to put those on the drawing. So next, once you look at your drawing, if it's a triangle problem, as you saw, chances are you're working with Pythagorean. Might be similar triangles, but the most common two are going to be your 30, 60, 90. So your 30, 60, 90 or 45, 45, 90. We use the 45, 45, 90 ratio in the roller skaters problem where they're colliding in an intersection. And we use the 30, 60, 90 for the equilateral triangle that was growing. And then we use Pythagorean even more than that, right? And then the similar triangles thing, it just doesn't seem to come up that often. And that seems like it's more for harder classes and AP classes. Your mileage may vary. Just go through your notes, look at your homework. Just start noticing stuff like this. Did my teacher either do any problems in class or make us do any problems that had similar triangles in them? The answer might be no, and then you don't have to worry about that shadow problem. But if you're doing similar triangles, that shadow problem is a classic. So if you don't see it on your test, I would be surprised. All right, and then ultimately, just like every other related rates problem, you've got to take the derivative with respect to t, be sure to keep everything in there, and then plug and chug, and you're done. I know, I make it sound easy. This is another one of those problem types where you just got to practice a lot, get good at it, see the patterns, see where you tend to go wrong, and memorize a way to plug and chug through it.